What are the chances of you knowing what this is? Yes, you got that right. This is a table. It's something that you use to organize data using constructs like columns and rows. However, did you know that a table is also known as a matrix? A matrix is a type of a multi-dimensional array and is one of the most popular data structures covered in coding interviews. In this video, I will discuss the most important aspects about matrices and how to implement them. Hi, my name is Ricardo Ferreira and I'm a developer advocate here with AWS. Welcome back to this series about data structures. In this episode, I will talk about matrices. The matrix data structure is widely used in many fields, such as linear algebra, computer graphics, and statistics. But I am almost sure that this is not the reason why you are here today. Chances are that you are here because, number one, you are a software engineer. And number two, matrices are heavily explored during coding interviews. Why matrices are so popular? Well, because they enable the efficient storage and manipulation of arrays. During coding interviews, developers are frequently required to solve problems involving two-dimensional arrays. And the problems vary from things like printing the matrix values in a form of a spiral to something even more elaborate like in place rotating the matrix by 90 degrees in clockwise direction. In addition, you may see sorting algorithms like quicksort being used along with matrix implementations. Overall, the matrix data structure is a versatile tool that frequently appears in coding interviews, therefore being an invaluable topic for you to learn while preparing for one. In this case, let's get to work. A matrix is a two-dimensional data structure that is used to store and manipulate arrays in a tabular form. It is made up of rows and columns where each element of the array is referred to as a cell. Imagine, for example, a spreadsheet where each row represents a record and each column represents a field or an attribute of that record. In a matrix, you can access individual elements by their row and column indices. In the spreadsheet example that I just gave you, let's say you want to retrieve the column first name. You could access the first name value for the first row by using the notation matrix 0 of 1, where matrix is the name of the matrix and 0 and 1 are the column and row indices, respectively. Matrix data structures are commonly used in mathematics, physics, and computer science for solving linear equations, representing graphs, and performing matrix operations such as addition, subtraction, multiplication, and transposition of data. They are also used in programming languages like MATLAB, Python, and Java for scientific computing and data analysis. Overall, matrices provide a convenient way to organize and manipulate data in a tabular format, making it easier to perform calculations, analyzing data, and represent complex relationships between variables. Matrices have several advantages. For example, a matrix data structure is a collection of rows and columns that are arranged in a grid-like fashion. The structure of the matrix allows for efficient storage and retrieval of data. It can also be used to represent and solve a wide range of mathematical problems, such as linear equations, vector spaces, and eigenvalues. It is a powerful tool for data analysis and visualization of data, as it allows for easy manipulation of data and the ability to see patterns and relationships between variables. However, just like any data structures, matrices have disadvantages. One of the main disadvantages of a matrix data structure is its size. A matrix data structure can be large and become unwieldy, especially if it contains a lot of data. This can make it difficult to manipulate and analyze data, especially if you are using a programming language that does not have efficient matrix operation support for it. Another disadvantage of a matrix data structure is its complexity. Creating a matrix data structure requires careful planning and design, and can be easy to make mistakes when you are designing the matrix. Additionally, modifying the data in a matrix can be time-consuming and difficult, especially if you need to modify multiple rows or columns. Let's see how matrices work from the implementation perspective. All right, back to our Visual Studio Code. We're going to start the implementation of our matrix in this class here called matrix, which you can find here on the package ADT. So the first thing we're going to do is to declare the matrix. So declare a matrix with 5 columns and 5 rows. So this means that we're going to create a perfectly square matrix. I'm going to hit enter. Let's see what Code Whisperer provides. Seems to be correct. Variable matrix. This is the matrix using the Java notation, which is one array within another array. And then these are the dimensions of this matrix. It's correct. And then we're going to, just like we did with the array episode, we're going to initialize this matrix with random values. So let's ask Code Whisperer to create a method to init the matrix with random values. I'm going to hit enter. Let's see how it comes. This method signature seems to be correct, or at least suggestive enough. I'm going to hit enter. Let's see what the code looks like. Looks correct. I'm going to close the method, but let me just review the method for a second. So here we have a outer loop that's going to iterate over the columns. And for each interaction, it's going to have an inner loop that's going to iterate over the rows of the matrix. So, and then for each column and row, it's going to associate a random value. So it seems to be correct. The only way for us to actually double check this is to print the values of this matrix. So let's create, here we go. Amazon Code Whisperer is kind of trying to anticipate what I want to do, which is create a method to print a matrix. Thank you, Code Whisperer. It's exactly what I need. So yeah, print a matrix. I am going to use this one here. Seems to be correct. And then, okay, it's probably doing some sort of indentation in the output. Okay, system println. Okay, I'm going to close it. Seems to be correct, but let's execute this method for the first time so we can check if it's doing what it's supposed to do. For this, I'm going to create a main method, and then we can go from there. So here we go. Yep, that's what I need. So instantiate the matrix, initialize the matrix, and then print the matrix. Let's execute this code for the first time so we can see the contents of this matrix, and more importantly, what's going to be the layout that this print matrix method is going to use. We're going to run, and then, okay, now I understand what the code is doing. So basically, it's doing this kind of a manipulation with the strings and spaces and checking if it is the end of the matrix, so we can start finishing that row. So it print out the values with this kind of like a table, right? Like a matrix that has like a bunch of rows and the columns. So, and as I mentioned before, since we're creating a matrix that has 5 columns and 5 rows, as you can see here is a perfectly square matrix. And the output doesn't seem like so perfectly, but it is. Like conceptually, it is a square instead of a rectangle, right? So far so good. It's definitely creating some random values on our matrix. Now, before we move further, it is important for you to know that what I mentioned before about it, sometimes when you're working with matrices, it's complicated, but it has to careful design of it. And what I meant by this is this. So when we were declaring the matrix, we had to do this conscious decision about how many actual columns and rows we were going to have. And then everything that happened further rely on the fact of this fixed size data structure. So this is one of the things that you have to keep in mind, because when you were creating one matrix for the first time and initialize with values, is going to sound just like you see here, a bit easy, because you know upfront what you're going to do. but the complexity of matrices start happening when you start mutating and adding on removing values. Let's see a couple of examples of this type of complexity. The first scenario we're going to play with is the scenario where you are asked to include into the existing matrix a new row. So the currently matrix has 5 columns and 5 rows, so you are going to end up with a matrix that now has 6 rows, and this new row is going to be initialized with random values. So let's see how this code and implementation would look like. So let's ask Code Whisperer to create a method to add a new row into the matrix and init the row with random values, right? So I'm gonna hit enter to see the implementation of this. Okay, let me start with the method signature, add row. I'm gonna hit enter, and then let's see what comes from this. All right, so there's only one suggestion, as you can see here, 1 of 1. So I'm gonna simply hit tab and accept this suggestion. So we are basically creating a new matrix. Like I mentioned before, dealing with the matrices is complicated because of the nature of their fixed size. So every time you are going to add or remove elements and columns and rows, you're most likely end up with the operation of recreating a new matrix, transversing the existing matrix, and copying the values to one and another. So this is an operation that takes time to compute, and depending on the size of the matrix, number of columns and number of rows, like I mentioned before, it can become computationally expensive. So this is one of the things that you have to keep in mind during the coding interview, right? And if the interviewer are asking you to perform operations like this, it's not only that you have to know how to do it, but you have to always keep that in mind, because in a given point in time, you might need to kind of change your approach for doing things. But right now, basically what they're doing is, after creating the new matrix, going to basically read the existing values and copy to this new matrix, and then doing some putting the and the new row that has been added is going to be initialized with random values, which is basically what we have asked in the instruction. So let's see how this goes. So I'm going to simply, after printing the original matrix, I'm going to put a separation here so we can see the difference of, and then we're going to matrix add row, right? So this is the row that's going to be initialized with random values. And then we're going to, once again, print the matrix. And as you can see here, Code Whisperer is already assuming that this is what we want to do. This is one of the things about like generative AI technologies, because giving a proper context and giving the proper set of instructions that you were given as a prompt for the generative AI implementation, it is able to do some inferences about what your intentions are. It is almost like a human-like prediction of behavior. It's very amazing. But anyway, let's execute this code one more time to see if this is doing what we are asking for. So here is the result of our first print with the square matrix. So square because it has 5 columns and 5 rows. And here you have the second one with the existing values, but now as you can see here, it has like 5 columns and 1, 2, 3, 4, 5, 6 rows. So it seems to be doing what you're supposed to do. So you just added a new row into the existing matrix, right? So if we review the code here, you're going to see that it involves the creation of a new matrix, the reading of the existing values. This is kind of optional because this is basically the result of us initializing with random values. And then we are basically doing the re-referencing of the new matrix to the old matrix. So it's basically for us to say, okay, the new matrix now has to be the one that has 6 rows, now the former one that has 5 rows. So this is one great example of restructuring operations that you can do in a matrix exercise. Now, The second operation that we're going to actually play with is removal of columns, right? So this is a little trickier because adding rows, it's somehow operation where you are basically dealing with the last dimension of a matrix, right? But now we're changing the first dimension of the matrix, which is the columns, right? So that's a little trickier. So let's see how this goes. So let's create a new method, create a method to remove the last column of the matrix, right? So that's a good instruction for Amazon Code Whisperer. Let's hit enter and see how it goes. Remove columns seems to be correct. The method signature is suggestive. And I'm going to hit enter and see what are the possible implementations. So basically, we're playing around here with two choices. One of them, iterate over the rows using the length, and the other one, length -1. I'm going to accept this version where length -1 seems to be more correct to me because, as you may know, arrays in Java, at least, they start with 0. So if you want to read the last position of array, you have to always remember that it is not, the last position is not going to be the size of the array, but size or length -1, right? So you have to compensate this fact that the arrays start from 0. So we've removed the column, and we're going to do the same exercise here. So we're going to create another separator to see how this goes. And then we're going to, yes, thank you, Amazon Code Whisperer. This is exactly what I want. I want to remove the column and then print the matrix one more time. So it's, let's see how this goes. I'm going to run the code one more time, and then let's review the output. So this is the first print. So we have the square matrix with 5 columns and 5 rows, seems to be correct. Then the second one, which it's we can assume it's correct because we didn't change that part of the code. So it's going to be like still 5 rows, 5 columns, and 6 rows. But in this version here, we're basically operating with a matrix that is similar to this one. You can see, but given the first columns, right? But it doesn't contain the last column, which is the column that contains the 4, 9, 0, 2, 2, and 1. So that last column was properly removed. Now that we see that the code works, and congratulations, Code Whisperer, because you were spot on this one, let's review the code. So always start with the creation of a new matrix. You can't get away from this. It's going to have basically the same length of the existing matrix, and the number of rows will be the length -1, seems to be correct. And then we're going to iterate over the outer loop, which is basically the number of columns that we have available. And then we're going to copy for each row only what is considered to be all the rows for each column. But as you can see here, because we're operating with length -1, we're not only going to copy the last column. So the implementation seems to be correct. And just like we did before, we are doing the dereferencing, which is the existing matrix is going to not only point to the version in memory. Remember, Java allocates all the objects on heap. So that object is going to be dereferenced. And then this reference called matrix is going to reference the new matrix. So we're going to retire the old implementation. So what's going to happen in Java, and by the way, this is one of the things that you also have to keep in mind about the architecture of certain programming languages and platforms. In case of Java, for example, there might be situations where the interviewer may come to you and say, hey, just out of curiosity, what's going to happen with this matrix variable after this code executes? So you should know that because of this whole like referencing and dereferences, what's going to happen with the original matrix is that it's going to be not only holding any references to it, so it's going to be electable for being garbage collected, because Java is a garbage collected programming language. So keep that in mind, because those are one examples of jabs that interviewers may come to. And they're not doing this because they want to be mean at you. They're doing to evaluate the depth of your knowledge into an existing programming language, or In a matter of fact, I would say that your depth of knowledge on computer architectures in general, because knowing how, for example, garbage collect works, it's important for you to be able, for them to measure you if you are a good developer in terms of optimizations and performance and things like this. So now that we have completed this exercise of structuring, let's play with some scenarios and examples that might happen in your coding interviews for you to play with the idea of manipulation of data. The first example is going to be actually pretty popular, which is imagine that we're working with a table, because again, matrix is basically a table. And then you were going to do that operation, that famous operation where you use your mouse and then you click on top of a column, right, where it holds the titles of the columns, and then you want to sort an existing column, specifically the column that you've just clicked. But for this exercise, you're not going to do any mouse and you don't have any visual representation of your matrix. Everything is conceptual, right? So the instruction is, how would you sort an existing column? Given a column, how would you sort that column in ascendant order, right? So let's see how this would look like in a code level. So let's create a method, which is going to sort the elements of a given column in ascendant order, right? So given a column, sort it in ascendant order. So let's see how the implementation looks like. So the method signature is suggestive. Not sure if you noticed, this is one of the patterns that when working with CodeWhisperer, it is interesting for you to know, because always start with the method signature, see if they make sense, because instinctively you might just want to kind of iterate over all the suggestion here. But I think it's always important for you to start with the method signature, because this is going to be your how you want the code to look like. So in my perspective, given the structure of the problem, I want to provide the column index. So that's my input, hence the parameter int column index, and the operation is sort the column. So the method signature seems to be correct, right? And return void means I don't want to return anything, I just want to sort, which is known in the algorithm space as a in-place operation. So why in place? Because I want to actually mutate the order of the elements within the data structure, right? So I'm going to accept this recommendation and hit enter so I can continue playing with the sorting exercise. There are two versions here. Both of them, no, actually there are 4 recommendations here. Let me iterate over each one of them and see which one we're going to use. This one is more like it, in my opinion, because dealing with matrices, you are almost going to end up in situations like this, where you need to iterate over at least once to read the values, and one or a couple more times to rearrange the position of the values. So you would never kind of be able to get away with the possibility of doing multiple iterations. And that's where comes the complexity of performance complexity of dealing with matrices, because now you are, regardless if you are changing the structure or simply doing in place mutations of data, you have to do those like continuous operations, right? So it's something that you have to keep in mind. So let's execute the code and then we can go back to read the algorithm. So let me kind of clean up a little bit of this. We don't need to inspect if the whole add row and removing columns are working. We know that is working at this point. So I'm going to remove kind of these operations. So in between init the matrix and print the matrix, I'm basically going to put the separation one more time. And then I'm going to request the matrix to, what is the name of the method? Sort column, this one over here. And then let's pick up maybe the first column, which is column number 0, right? And then we're going to print the matrix again. Yes, thank you, CodeWhisperer. This is what I need. I'm going to clean up this output a little bit, and then let's see if this is working, right? So let's run the code one more time. and inspect the output. So here's the first output. Nothing is supposed to change here. It's just a matrix with 5 columns, 5 rows, random values. But we've asked it for the first column to be sorted. So let's see if this happens. So the first column is 95028. And the second version, the first column is 02589, which is a darn good sorting in my opinion. So this is the correct output that we were looking for. So now that we know that the code is doing what it's supposed to do, let's go back and review the implementation. So sort column given an index. What we're going to do is create a new version of the sorted array given the length of the existing matrix. And then we are going, and again, why an array with only one dimension, or in other words, an array? Because it is almost as if you were zooming in into one of the dimensions of that matrix. So remember, a matrix is nothing more than an array whose the elements of the first dimensions is another array, right? So before we move forward, let's see this, how this works visually. So I'm going to put a breakpoint here, and then we're going to debug the code so we can use the debug visualizer, right? So let's work with the debug visualizer. So debug visualizer, this is new, and then we're going to simply use the matrix, right? So this is a better way for you to visualize the matrix. So as you can see here, the matrix has 5 columns and 5 rows, and each one of those dimensions, let me zoom in a little bit here. Let me give you more space for you to see. Let's see, for example, the first dimension, which is this one, 0. So in the first dimension, which is the first column, the result of this dimension is another array. So this is the interesting thing about using the debug visualizer for you to see this more complex visualization of your matrix. So if you look at it from this perspective, what we are using here in a sorted array is essentially we are capturing this array over here. We're focusing and zooming in into only one dimension of that matrix, which is the first column, right? It could be any one of these other matrices over here. The difference between this one, 0, and this one is that this is the first column and this is the second column, right? So since we've requested the 0 one, which is represents the first column, that's the array that's iterating over. And then it's essentially going to perform, let me resume the debugging execution. So what's going to happen here is that the code is going to read all the elements of the first column and then is going to perform the sorting. And if you remember the episode of arrays, and if you look here to the suggested code, basically what this code is doing is an implementation of the algorithm called bubble sort, right? And why is easy to remember? Because bubble sort, its characteristics has a simpler implementation, is essentially a nested loop of some sort of, and that is basically swapping the elements. And then we're going to, once this inner loop new created array is sorted, we're basically going to replace the elements of the existing matrix with this sorted array. So again, create a new array, read the existing values, do the sorting, and then we're going to do an in-place replacing. Is that the proper way to do it? Let me know here in the comments that if the way I said that out loud is correct, but it seems to be the case. It sounds redundant, but it isn't. Like we're doing in place, meaning that we're doing inside the structure, replacing of the values, right? So seems to be correct. Now let's do another interesting exercise that has to do with data visualization as well, but has to do with how we're going to print the values of the matrix, right? One very popular problem that interviewers like to explore in coding interviews is how you can think of a matrix in terms of like dimensions. First of all, like a matrix. What is a matrix? Is a two-dimensional array, right? The first dimension is the columns, the second dimensions are the rows. So the problem statement usually like create an algorithm that's going to print the values of the existing matrix, very similar to what we have done here, so the print matrix, but This is what we call printing the values of the matrix in their natural order, right? So the way they are sitting there in the matrix is the way it is going to be printed. The problem statement that interviewers like to explore is print the values of the existing matrix in a spiral order. So spiral is that shape that going like different circles that keep like getting smaller and smaller and smaller. And then that is the type of output that they want for you to implement the algorithm to. So let's see how the implementation goes. I'm going to execute the code so you can see what a spiral looks like, and then we can review the code from that, right? So I'm going to create a code here right below the print matrix method. I'm going to use Code Whisperer to create a method to print the matrix values in a spiral format, right? So I'm strictly giving the directions about what I need to do. I'm going to hit enter, and then let's see how the implementation goes. All right. Yep, print spiral. The method signature is correct. I'm going to hit enter, and let's see how this goes. Code Whisperer is thinking about what to suggest. Okay. All right. The implementation sounds a bit sophisticated, but since we have actually 4 suggestions of it. So 1, 2, 3, and 4. Okay, this one doesn't look what I need, but this one here sounds to be what we need. So I'm gonna get that one. We can always accept one, and then if it's not correct, we can simply go back to the other one. I'm gonna hit enter. Okay, okay. I'm gonna hit close this one, and essentially it's printing this. So the only thing I'm going to do is removing this printing here, right? No, actually, I don't need to remove this printing, because what this method, that's the interesting way for you to work with Amazon Code Whisperer. You gave it your intention, you accepted the implementation, and at a given point in time, your mental model is going to think, oh, no, I'm going to get rid of this like whole printing here. But again, Code Whisperer is doing this suggestion for a reason, because, hey, you want to print this, right? So this is Code Whisperer suggesting that you have to kind of give some row spaces in between each interaction of the loop. So I'm going to keep this suggestion. I'm going to trust Code Whisperer that is going to do what it's supposed to do. Just like we did before, let's skip the reading of the algorithms for now. Let's just see how this goes, and then we can go back to the code. Let me go to the main method here. I'm going to remove this breakpoint. And then in the main method, let's actually remove the sort column. We've verified the sort column is working as expected. So instead of this, we're going to print matrix, print spiral. Yeah. That's what we need. And we're going to remove that last print matrix. So what the code is doing now is create a matrix, initialize, print the one. Again, like I said, printing in this natural form, and a space for us to see the difference visually about the difference, and then print in a spiral. Let's clear the output and run the code to see if it's doing what it's supposed to do. We're going to click run, and then, all right. So let's see how this is doing. So if you look, this is how you should look on a spiral in a matrix. So a spiral is basically going to start reading the elements like this. It's going to 5, 3, 9, 4, 8, which seems to be the case, 5, 3, 9, 4, 8. And then once it hits the end of the last column, it's going to start reading down. So 8, 9, 8, 1, 4. So 4, 8, and then 9, 9, 8, 1, 4. So it's reading right here down. And then the next one's going to be like this, 7, 2, 1, 2. So 7, 2, 1, 2. That sounds correct. And then once it hits the beginning of the matrix, it's going to be 4, 9, 2. So let me, 4. So here's the thing. It's not 4. Okay, I lost my count. So 2 and then 4, 8, 3. So what is doing here? 4, 8. Oh no, here, yes. So that's correct. So now it's going to do a transverse 4, 8, 3. See here? And then it's going to 7. Yes, 4, 8, 3. Now it's kind of a like in a diagonal or orientation. So 4, 8, 3 is doing like this, right? So here's the count: 4, 8, 3. And now 7 to 9. So 7 to 9. So now it's going down again. But look, now you're not going down considering the last column. It has to be one column before, because the last column has been read in the first interaction. So it's the spiral. Remember, it's supposed to be going down and going inner in the loop. So 7 to 9. And then it's going to 2, 4 go up again, right? So 2, 4, which is this one and this one. So it did this exercise beautifully, which is doing this, doing go down, go this, going a transversional, and then moving to the right center, which is the last 4 over here of the matrix. So that's what an spiral printing of the values of a matrix look like. So remember that you have to kind of do this exercise. When you look for the implementation of the algorithm this way, visually, right, it starts to make more sense. One of the things that at least is tricky for me when I got like questions like this in a live interview especially, is that you have to be like a very articulated with, and first kind of imagine data algorithms, data structure is ultimately an exercise of imagination. Or you have to imagine how the structure and the output would look like, and then you go from there, right? So always when you are studying algorithms, the structures, try to do this kind of imagination exercise. Imagine the data structure, imagine this representation, imagine the structure. And this is where the debug visualizer can help you a lot with some data structures. But now that we've seen that the output is correct, let's go back to the implementation and review the code. So essentially, let me get rid of the console for a second. It's taking too much space. All right. Okay, so what the code's doing is, all right, it have variables for you to remember what is the row start and the column starts, and where is the column end and the row end. So it always have kind of these reminders about where you already read, and then you have to kind of move inner and inner. So there's going to be this kind of outer loop that's going to always keep reminding, okay, keep in mind that after every iteration, you have to keep getting away from the edges of the rows and the columns. So it's always checking if the row is the end of the row or the column is the end of the columns. And then you are going to have inner loops to transverse either a given column or a given row that you were reading. And then it's going to kind of change and mutate these reminders here to kind of keep adjusting the precision of your spiral iteration. So the algorithm seems to be doing what it's supposed to do. So it's doing fine. Now let's check one more kind of a problem that you may see in a coding interview. And it seems to be like a complicated problem, but you're going to see that's one of the most obvious one that you can possibly be able to solve, right? So the problem statement is usually started like this, like how would you check if the matrix it's a square one, right? So in the beginning of this the implementation part, I kind of gave away what a square matrix looks like. And a square matrix, for you to know, is basically a matrix where the number of columns match the number of rows. So basically what your algorithm is supposed to do is to check if this equals to this. It's that simple, right? So let's see if this is the case. I'm going to ask Code Whisperer to create a method to check if the matrix is a square one. I think that's a good problem statement. That's going to be the right prompt for Code Whisperer. So I'm going to hit enter, and yep, exactly. This is it. So is square is basically is going to check if the matrix length is, which is the column, right? Numbers of columns. Remember, the first dimension of a matrix is always the columns. And then it's going to check if it matches with the first row, which is another array. And it's going to check the length of this array if it matches with the number of columns. So if it matches, yep, it's a square. So I'm going to do this. I'm going to remove print if it's a spiral, and I'm going to simply, nope, I want to print spiral matrix and then check if it says a spiral. Yes, matrix is a square, not spiral, it's square matrix. And I'm going to put a question mark here. Like if I'm asking, is it square or not? So let me execute the code, and then it's going to print it and say, is a square matrix true? Yeah, because it has 4 columns and 4 rows. Now, let's go back to that implementation where we've added a new, which one we had, which exercise we've removed a column, right? Yes, let's pick this one. Let's remove a column after checking if the matrix is a square. So matrix dot remove column. So we've just removed a column. We've changed it. We did an in place changing of the structure of the matrix. And then we're going to ask again if, considering this new mutation of the matrix, if it still look like a square matrix, right? So recap the implementation. We're going to print it, and then we're going to ask if it's square. We're going to remove the column and then see if this still holds true. So let's clear the output, and I'm going to click run. And yep, seems to be the case, right? So it first created a matrix and initialized with the values. It is a square matrix, true, and then we remove the last column. And why it's saying here that's false? Because now, since we've removed the column, this value here is going to be smaller than the result of this value over here. So this whole verification here will return false. So it's a simple implementation, right? You basically are comparing the length of the number of columns with you retrieve the first row of that matrix, and then you compare the length of it with the number of columns. But it is a powerful verification because the interviewers want you to verify how much you can like create this mental model of not only kind of visualize that what is a square, what is a non-square matrix? Like a non-square matrix, let's say you have a table with 5 columns and 20 rows, right? So mentally and visually, this is going to look like more like a rectangle, right, than a square, right? Because it's going to be like this, like this number of columns, but a very long number of rows. Or it can be the other way around. You have like 3 rows and a bunch of columns. So still it's going to be like a rectangle. A perfect square matrix is the one we have 5 rows, and then you're going to have like 5 columns, and then you're going to have like 5 rows. So this is how you verify visually. But more importantly, it also wants to, the interview wants you to know, verify how much you know how this visual representation looks like in a structure level, because you're being tested and understanding of the matrix data structure. Let's wrap up what you have seen in this episode. Matrices are a 2-dimensional data structure used to store and manipulate arrays in a tabular form. It allows for efficient storage and retrieval of data. Just like arrays, adding and removing elements require changing the structure of the matrix because their size is fixed. This is particularly true for large matrices containing many rows, where adding a new row becomes computationally expensive. Therefore, matrices are ideal for scenarios where data is read-only, such as calculations and data visualization. My suggestion for you is to keep practicing different sorting algorithms with matrices and use Amazon Code Whisperer to assist you with the code generation. Then spend some time studying the generated code and whenever applicable, criticize and correct the code. In the next episode of this series, we will take a look at the notorious linked list. If you started watching this series from the playlist, the next video about linked lists should start pretty soon. If not, I put the link of the next video in the description below. See you in a bit.